All right, class. So I left you with this take-home problem last time. And then, so on the exam, when I give you the problem, I will also give you all the concept. This is exactly what you would get on exam. Now, so this was a problem. And what this problem is asking you is that you have 18 grams of water and the water is solid at minus 10 degrees. You know at minus 10 degrees it would be solid. And you want to convert it to gas that is at 110. So it's not just phase change, we also have a bunch of temperature change going on. If you remember, we had this graph last time, right? We have this graph, and I want to quickly go over this graph again to make sure you understand it. So here, this is heat getting applied, and this is temperature. So when you have ice, you're going to, any kind of solid, you're going to apply heat. When you apply heat, the temperature is going to increase, right? The temperature is going to increase. So I'm going to have solid here. I still have solid, right? So all my energy is going to go to T change. But once I reach zero, then if I apply more energy, that energy is going to go to phase change. And the solid is going to turn into liquid. Okay? So again, I apply energy, the energy goes towards T change. Once I reach zero for water, then if I apply more energy, then it's going to be a phase change. Solid is going to go to liquid. Then I'm going to apply more energy. Now that everything has been converted to liquid, that energy is going to go towards T change. When I get up here, this is still liquid. Now, once I reach 100, and this is 100, once I reach 100, if I apply more energy, then the temperature is not going to change. All is going to happen, I'm going to have a phase change and liquid is going to go to gas. You already know that. If you take a kettle, put water in it, heat it up, once it reaches 100, you cannot get the water to be hotter than 100. It will just evaporate and it goes to the gas phase. And then if you keep heating it up, yep, I can have temperature change, and that's why water vapor is really, really hot. So T change and P change cannot happen at the same time. Just think about this. T change, P change, T change, P change. And you can have phase change at a specific temperature. For water, that is 0 and that is 100. That's when the phase can change. All right. Now, the other thing I ask you to put on a piece of paper when you're doing practice problem is that this phase change, solid to liquid, liquid to gas. When you come down, that's an endothermic reaction. When you go up, that's an exothermic reaction. You already know that if you have water liquid, you have to apply energy. You have to heat it up to go to gas. So it's an endothermic reaction. You need energy. And this one is exothermic reaction. All right, now that we have this, let's go back here. So here our problem, where are we at? And where are we trying to get to? So where we are at minus 10 degrees, and we're going to try to go to 110. So we are right here, and we're trying to get all the way to up here. This is where we're trying to go. We're trying to go from here to here. So the first thing that needs to happen is a T change. So we're here trying to go over there. You can't just jump. You have to go through the hoops. The first thing is a T change. That's the first thing. Then we're going to have a phase change and then so on. So the first one is a T change. You know the equation for T change. Okay. So energy is going to be equal is mass, which is 18 grams. Now, right now, this is ice. So I have to use the specific heat of water solid, which is 2.06 joules over gram degree Celsius. Okay, so it's mass times the specific heat times T final minus T initial. What is my T final? Again, let's go back over here. So I'm at minus 10. I'm trying to go to 0. I'm at minus 10, trying to go to 0. And I have to use a specific heat of water solid, because right now this is solid. Okay, so my T final is going to be 0 minus my T initial is 10 degrees Celsius. If I do that, I get 371 joules of energy. Now what happens is, right now I am at 0 degrees. When you are at 0 degrees, then what could be happening? Then phase change could happen. When you are at 0 degrees, then phase change could happen. Now the solid can go to liquid. So what do we have next? The next thing we have is a phase change. Mass, which is 18 grams, times now the phase change, solid going to liquid, solid going to liquid, that is fusion. Solid going to liquid, that is fusion. Okay, so 333 joules per gram. What I end up getting is 5,990 joules of energy. Okay, now where am I? I'm right here. Everything has been converted to liquid. Now if I apply energy, it's going to go towards T change. Okay, so our next thing is T change. So I have 18 grams. Now what am I? Right now I am at liquid. So the specific heat of water liquid is 1.84 joules over gram degree Celsius, because water, specific heat of water for liquid, solid, and gas is different. Make sure what you are. And then what is my T final? Let's go back here. I'm right here. I'm trying to go to 100. So my T final is 100. What is my T initial? 0 degrees. What I get for this T change is 7,530 joules. Okay, now what's going to happen? I am at 100 degrees Celsius. If you are at 100 degrees Celsius, P change, phase change can happen. Now I can go liquid to gas since I'm at that temperature. Okay, so we have to do a P change. Is 18 grams. Now liquid to gas, that is heat of vaporization, right? Liquid to gas, that's the heat of vaporization. So that's the number. Again, I will give you all the constant. You don't have to really memorize them. 2,260 joules per gram. Okay, what I end up getting is 40,700 joules of energy. Okay, now that everything has been converted to gas, where am I? I am right here. If I apply more energy, then I'm going to have a T change. Now I'm going to have a T change. This is a really long problem, but it's good. It has a little bit of everything. So now I am gas. So I'm going to use a specific heat of water gas. That's really key. Now the temperature I'm trying to get to is 110. My initial temperature is at 100. So what I end up getting is 365 joules of energy. All right, what do you think you have to do next? So I figured out in each step how much energy I need to get there, right? Each step, how much energy I need. Now the question asks you to get from here to here, how much energy is released or absorbed. So what we have to do, we have to add them up. What we're going to do, we're going to add up all these numbers. We're going to add up this number, this number, this number, and this number. We're going to add them up. If you add them up, what you end up getting, again, I'm limited to 2 sig fig, I get 55,000 joules of energy. Now, is a positive number. What does that mean? That means it's an endothermic process. So energy is required to do this. And you already knew that because we said when we go this way, usually energy is required. When you go the other way, energy is released because we are going this way. Energy is required. Okay. All right, that was a big problem. Now, let's do another problem similar to this. So here's our next problem. Pause my video and then do this problem, and then we're going to go over it together. And every time I have a tendency to draw this, it helps me a little bit to see where am I and where am I trying to get to. Alright, so hopefully you pause me and you do this problem. So how much energy is released or absorbed when you convert 10 grams of water liquid at 10 degrees to ice at 0 degrees? So where am I on this chart? On this chart, I am right here. I'm somewhere right here, okay? And I'm trying to get over here because this is my 0 and this is my 100. So I'm right here. And I'm trying to get to ice at 0. I'm trying to get to over here. So what do I need to do? I need to do a T change and I need to do a P change, right? I need a T change and I need a P change. Again, I'm going to tell you how I got there. So you have water liquid at 10. So here would be, this is about 10. And then I'm going to go to ice at 0. This is liquid at 0. This is ice at 0. Now, so I have to do a temperature change first. You know how to do a temperature change first. I will have to, and the other thing I always want you to put down is this. Don't forget solid, liquid, gas. You come down endothermic, you go up is exothermic. Alright, so my first one is a T change. Energy is going to equal mass, which is 10 grams. Specific heat, what am I? I am liquid, so I use a specific heat of water liquid, which is 4.184 joules gram degrees Celsius. What's my T final? I'm trying to get to 0. What is my 10 initial temperature? Initial temperature is 10 degrees. So when I do this, I get minus 418 joules of energy. Okay, now that I am at 0, what can I do at 0? P change. Phase change can definitely happen at 0, right? So phase change can happen at 0. And remember, what I'm trying to get to, this is the P change I'm trying to get to, liquid to solid. All right. So P change, I know the equation for P change is equals mass, which is 10.0 gram. Now, what is my P change here? I'm going from liquid to solid. If you go back here, all the information that I gave you, heat of fusion was 333. So heat of fusion is when you go from solid to liquid. That was this number. Now, I'm going the opposite way. I'm going from liquid to solid. Remember, the distance is the same. So it's the same number, except now I'm going to be releasing the energy. So this one over here is negative 333. I will explain that in 1 second again. So the way I explained it last time to you guys, if I go up and down, it's the same distance, only the same amount of energy, just that when I come here, I require it. I go the other way, I release the energy. So if I do this, what I end up getting is negative 3,330 joules of energy. So we talked about it last time. What you have to do, you have to add up the number. If you add up the number, you get negative 3,750 joules of energy. And what is this? This is an exothermic reaction. Energy was released, which is kind of what I expected because we talked about it here. That if you go this way, usually you are applying heat. You go the other way on the graph, you are releasing heat. So heat is released. All right, nice job. Now, we have plenty of time. Let's do another practice problem. Here's our next practice problem. Okay, read this question, pause it and read this question. We're getting a little bit fancier, which is good. We want to get fancier. Now, so you're gonna pause this and read this. In this chapter, all the questions we do, try to draw it out. You have no idea how much is gonna help to draw this out. So what is going on? Here I have a beaker, right? You may not be as talented as I am in drawing, but you can still try. So here's my beaker, and here's my water in here. This is my water, okay? Now, how much water do I have? I have 1 liter of water. You guys agree? Okay. Now, what I have I have a piece of iron, okay? And what I'm going to do, I'm going to heat this piece of iron and I'm going to add it to water. So I'm going to heat it and I'm going to add it to water. You guys are following me so far? When I do that, the temperature of water at the beginning is 20 degrees and that temperature is going to rise to 32.8 degrees. That makes sense. If I heat up a piece of metal and I add it to water, of course, the temperature is going to get hotter, right? The temperature is going to increase. And I ask you, what was the original temperature of this iron? How much did I heat it up with when I put it in the water? So there is no phase change here. Do you agree? Nothing is changing the phase. The only thing that is changing is temperature, right? I'm going to heat up a piece of iron and I'm going to drop it into this water liquid. The temperature of water before I dropped the heated iron was 20. I dropped the hot iron in here. The hot iron metal is going to go to 32.8 degrees. So there's no phase change. But what's going on here, this is really, really key. There's a transfer of energy. There is a transfer of energy. When I heat this up and I add it to this very cold water, what happens? Iron is going to lose energy. Who gets the energy? Water gets the energy, and that's how water is going to get hot. And that's how water is going to get hot. So I'm actually going to write this down because this is very key, that iron is going to lose energy. Who gets that energy? It's a transfer of energy. If one person or one thing lose it, the other one has to get it. And then water is going to get the energy, and that's why it got hot. It's going to get the energy and it's going to get hot. So what's going on here? What's going on here? I have a transfer of energy. I have a transfer of energy going on. And there is no phase change. It's just a temperature change. Okay. So now, if it's temperature change, I have to use the temperature change equation. Energy is equal mass times specific heat. That's my T change. Times T final minus T initial, right? Every time I have a temperature change, this is the equation that I have to use. Let's plug it in. We got this. So, what is the mass of water? I said I have 1 liter of water. You know that density of water is 1. Density of water is 1. What does that mean? What does that mean? That's really, really key to kind of think about this. I want to actually put it on this piece of paper. Density of water is always 1. What that means is if I have 1 ml of water, that's 1 gram. If I have 2 ml of water, that's 2 grams. Think about this because density of water is 1 gram per milliliters. So here, what I have 1.00 liter of water. I can think about in terms of milliliters because density of water is 1 gram per ml. So 1 liter is 1,000 milliliter, which means is 1,000 grams. And that's what they give you the density. Every time they give you a density, you can convert volume to mass. I need you to remember that when you move on to Chem 1B. Make a note of it. Every time they give you a density, that's the way you can convert volume to mass. So here I have volume of water. I have a density of water. I can convert it to mass of water. Alright, so what that means is mass of water is 1,000 gram. This is specific here of water liquid, 4.184 joules over gram degrees Celsius. All the units are great. The final temperature of water was 32.8, right? The water was originally 20 degrees. If I add it, it went to 32.8 degrees. So what I end up getting is 53555.2 joules. And it's a positive number. Okay. Now, what does this number tell me? What does it tell me? Water got this energy. Water got this much energy. Okay? Water got energy. And this is how much energy water got. And after water got this much energy, and then it got warmer. It became warmer. So water got this much energy, 50,555.2 joules of energy. Now, if water got this energy, what does that mean about iron? So again, water got this much energy. That's why it got warmer. Now, if water got this much energy, that means who lost this much energy? That means iron lost this much energy. Again, water gets it. That means iron has to lose it. And I know water got it, not just because it got hot. Also, look at the sign. Sign will tell you too. It's an endothermic reaction. Water got that much energy. If water got it, who lost it? Iron lost the energy. So, there's no phase change going on. And you were trying to figure out again, what was the question? What was the original temperature of iron? Okay? So, we have to do another T change. How much iron did I have? 400 grams of iron. The specific heat of iron is 0.451 joules over gram degrees Celsius. What was the final temperature of iron? 32.8. They both reach the same temperature because, one loses, one gain, and they're both going to have the same temperature. And I don't know what is the initial temperature. That's what I'm trying to figure out. Okay? Again, we know that what happened is I heat this up. I don't know how much I heated it up. I added it here. But the final temperature of water and iron was 32.8. So what I'm trying to figure out is this one right here. That's what I'm trying to solve. Now, I cannot have two variables. That's not going to happen. But I don't have two variables. I know the energy. How do I know the energy? Back over here. Water got 53,555.2 joules of energy. What that means is iron lost 53,555.2 joules of energy. It's a transfer of energy. One loses, the other one is going to gain. Now, this is very key. Iron lost the energy. So it's minus 53555.2 joules of energy. This matters. If you don't put that in, you're not going to get the right number. That one matters. That one matters. Okay? So that one matters. Now, the math can get a little tricky. Not tricky, it's just algebra. But make sure you go through the math. And I'm actually going to go through the math with you just in case to make sure that you get it down. So again, what we have here, we have 400. You know what? Let me go to next page so I have plenty of room to show you. So we had 400 grams times the specific heat, which is 0.451 joules grams degrees Celsius. And then the T final was 32.8. And I'm trying to figure out the X. And we know that that this much energy was lost by iron. Okay? So then the way that I'm going to do the math, again, there's many ways to do the algebra. What I'm going to do, I'm going to multiply this together. I get 180.4 and times 32.8 minus X equal minus 53,555.2 joules of energy. Okay. Now what I'm going to do, what I have to do is to multiply this out. So then what I get is 5917.2 minus 180.4x. I know you know the math, but I just want to make sure we're on the same page. Alright, that's not bad. Now what I'm going to do, I'm going to move this to the other side. So all the variables would be on one side and all the values would be the other side. So then it would be minus 59472.3, because when you move it to the other side, it has to be minus. Now I can finally, again, I was trying to solve for x. I can finally solve for x. It would be minus 59472.3 divided by 180.4. What I end up getting is 330 degrees Celsius. That was the original temperature of iron. Again, the key to this was that there was no phase change. It was a transfer of energy. It was a temperature change. One lost energy, one got their energy. And you have to be very careful when you get the energy is positive. And when we did the calculation, we got positive. You know, water got the energy, which means that iron had to lose the energy. Don't forget to put a little minus there. Otherwise, you're not going to get the right answer. All right. Very nice job. I will talk to you guys next time.